Let us set up the stage and pose a question for today. We have X, a parent population with a mean mu and variance sigma squared, the standard notations. We don't know if the population X is normal or not, and it doesn't matter. We want to explore ways to estimate the variance of the population from a sample. What we generally do would take a sample of size n. To take a sample of size n, we imagine that we multiply the parent population and we have n copies of the parent population. So we take one element, x1, from the first copy, a second element from the second copy, and so on. So we end up with a sample which is going to be x1, x2, xn. This is our notation for the sample. With this sample, we can explore the mean. If we discussed earlier how if for all possible samples we calculate the sample mean, we create a new population, which we denote x bar, and it's called the sampling distribution of the mean. Distribution containing all sample means. One element of this population is x small bar, which is a sample mean. We also saw how this one is an unbiased estimator for the population mean, meaning that if you take one sample of size n and you calculate its mean, you can use that number to estimate fairly confidently the population mean. We ask ourselves today, what if I calculate the variance of the sample? Will the variance of the sample be a good or unbiased estimator for the parent population? Variance, not mean. So I repeat, if we take a sample of size n, and for that sample we calculate the sample variance, the question is, will this variance of the sample be an unbiased estimator for the parent population variance? Can I use it to estimate the population variance? So let's answer this question. We are going to use the following results. The sampling distribution of the means is normally distributed with the mean mu and the variance sigma squared, same as the variance of the population. And we are going to use a formula for the variance of x as being the expected value of x squared minus the mean squared for any x. Therefore, we can use the same relation for the variance of the sampling distribution of the means. Okay, so let's answer our question. I will rewrite the formula for the variance by opening the bracket. Remember, these xi are the elements in the sample, and x bar is the mean of the sample. So I open the bracket using the quadratic formula, and then I reorganize my elements inside. So what do I have in this sum? For I equals 1, I get x1 squared minus 2 times x bar x1 plus x bar squared, and so on. Instead of adding all these numbers on the horizontal, I'm going to add them on the vertical. First this column, then this column, and I can factorize a 2x bar. And in this column, I have n times the mean of the sample squared. Now, if I put the 1 over n inside, I get this expression. As you see, this is the expected value of x squared because each value is squared. So it's a mean of this set. Minus 2 times the mean times, and that's again the mean. So I get the mean squared plus the mean squared. So I get the expected value of x squared minus the mean of the sample squared. Now this expression is difficult to evaluate, so I'm going to use a formula on the previous page to replace it in terms of the variance. So these two terms are the same as this one here.